Hi, everyone. My name is Alexander. Thank you for coming. I'm going to talk about a scalable implementation of deep learning on Spark. It is a joint work with Changuri Meng from Databricks, Berg Drevenbosch from Huawei, Guohan Li from Spark Community, and Andrei Simonovsky from Hewlett-Packard Labs. Four of us didn't know each other until we met on the Spark developers mailing list. And Spark actually was a platform which enabled us to collaborate and to do some good development and research on a common platform that actually beneficial for everyone. The outline of my talk is as follows. I'm going to talk about the basics of artificial neural networks. Then I'm going to focus on the implementation of multi-layer perceptron in Spark and how we did optimization and parallelization. I will conclude with experiments and future work. And since this talk is based on the talk on Spark Summit, on the recent Spark Summit, I also list here what is new comparing to my previous talk. So first of all, I added some slides about the parallelization heuristic that I'm going to talk about. And also, I did some new experiment with larger cluster. And also, there is a new slide design. Actually, now it's Hewlett-Packard Enterprise. Probably you know that HP split into two companies. So now I'm in the green one. So artificial neural networks. It is a statistical model that approximates a function of multiple inputs. It consists of interconnected neurons, and they exchange messages. Neuron produces an output by applying a transformation function on its inputs. And neurons are usually grouped into layers. A network with more than 3 layers of neurons can be called deep. It can be an instance of deep learning. And on the right-hand side, you can see a small example of neural network, which has 2 inputs, 3 neurons in the hidden layer, and 1 output. There are different types of layers, and layer type is defined by a transformation function. The most common is affine transformation, when you multiply the input by some weights and then add bias, and sigmoid, which transforms the input into the interval 0, 1, which might be very useful for classification purposes. You see the shape of the function on the right-hand side. Also, there are such layers as convolutional, softmax, etc. Multi-layer perceptron is a network with several pairs of affine and sigmoid layers. And model parameters are the weights that neurons use for transformations. And those parameters are iteratively estimated with the backpropagation algorithm. And multi-layer perceptron currently is widely used for speech recognition, in particular for phoneme classification, and in computer vision as a top layer of the network. And multi-layer perceptron was released with Spark 1.5. So it is in the main distribution, and you can use it already. So first of all, let me show you a simple example how to use it in Spark. So assume that you want to build a very simple classificator that classifies the input images that classifies the handwritten images into digits 0, 9. So it's actually a very famous data set called MNIST. It consists of the grayscale images of 28 by 28 pixels, and they represent digits. So then we need to build a multi-layer perceptron with 784 inputs as the number of pixels, and 10 outputs as the number of different digits that we want to classify. And also, we can add 2 hidden layers that would provide better accuracy as suggested in this paper. And the network would look like on the picture. So it has 784 inputs and 2 hidden layers, and then 10 outputs. To do this in Spark, you need to do the following. So first line, it loads the dataset. Second line creates a classifier and sets the layers and the block size. I'm going to talk about it later. And then the last line, it trains the model. And after that, you can use this model for prediction. And the similar thing you can do in Python. So basically the same 3 lines of code. So it's very simple. You can also use multi-layer perceptron in Spark pipelines. Like, for example, on this screen. We also load the dataset in the first line. Then we create a PCA transformator that extracts 20 features from the dataset. And then we use those 20 features for classification. So it is the third line. After that, we create a pipeline of PCA and multi-layer perceptron and train the model. And the same can be done in Python. So basically, it is to show that multi-layer perceptron supports Spark pipelines, which are quite useful. So now let me talk about the implementation itself and the problems that we faced. So we addressed 3 main requirements in our implementation. First of all, we conform to Spark APIs. Then we wanted to provide extensible interface so that other people can use it. And also, the perceptrons should be efficient and scalable. Just it should be fast. So why conform to Spark API? Because Spark can call any Java, Python, or Scala library, not necessarily designed for Spark. So actually, you can use any Java or Python library that has multi-layer perceptron and call it from Spark. But this approach has some problems. So first of all, it results with expensive data movement from Spark to the library. And second, it prohibits from using this library in Spark machine learning pipelines. So we addressed this requirement. Second, it should have extensible interface. So since Spark is open source product, then probably other people would like to contribute and would like to write new layers or new functions, new features. So we had to write extensible interface and easy-to-use interface for developers. And our implementation processes each layer as a black box in backpropagation in general form, so that it is easy to implement new layers and features. So we basically need to implement a rather simple interface. And currently, there are several features under development. In particular, convolutional neural networks, stacked out encoder, restricted Boltzmann machines, and others. The last requirement was about efficiency and scalability. The efficiency was addressed by batch processing. As I mentioned, multi-layer perceptron consists of several layers, several pairs of affine and sigmoid transformations. And affine transformation can be represented in vector form as follows. So it's basically a multiplication of weights by the input and addition of some bias. And it can be represented in this way, like on a picture. But vector matrix multiplications are not as efficient as matrix matrix. And then we can do batching. So we can stack as input vectors into batch and perform matrices multiplication. And that means that the variables in the equation, they just become matrices with corresponding dimensions. And it can be represented on this picture. So it's basically, instead of multiplying matrix by vector, you multiply matrix by matrix. And in this way, you can gain performance. and it's very simple. So we implemented batch processing in matrix form, and that enabled the use of optimized native BLAS libraries. I will talk about them on the next slide. And we also did some optimization so that we limit the GC overhead. So we try to reuse the memory all the time. So what is BLAS? BLAS is basic linear algebra subprograms. It is a hardware-optimized natives in C and Fortran. There are several famous implementations like Intel MKL, OpenBLAS, which usually comes with the Linux distributions. Also, there is an interface for GPU called NVBLAS, and it's different from CUDA BLAS because CUDA BLAS is not a standard BLAS implementation, so it's a little bit tricky. And in Spark, we can use BLAS through the netlib Java library, which is bundled with Spark. And to use the binaries, we need to compile Spark with specific flag, but it's also very simple. On the screen, I'm showing the performance of the matrices multiplication with the use of different BLAS libraries. So on the y-axis, there are seconds, and it's logarithmic. And on the x-axis are the matrices sizes. And with different colors, I show the different libraries. And it's obvious that there is a huge benefit from native BLAS comparing pure Java F2J BLAS. So if you want to use some linear algebra, you probably should compile Spark with specific flag and use native BLAS. So you can see that the dark gray line is kind of very slow. So it multiplies matrices in a very long time. And surprisingly, GPU is faster only for large matrices. It is the light green line. And it is due to the fact that when we use NVBLAS, which is an interface for GPU BLAS, we do a copy from the DRAM to the memory of the GPU. And when the computation, then the actual multiplication takes a long time, then this transfer from memory to memory, it seems to be slow. It seems to be little comparing to the computation. And if the computation is very simple, then you just spend a lot of time on transferring. And that's why that's why GPU is only good here for large matrices. But still, you can gain some performance. Also, there are more details on this site and in our recent paper. So it has more experiments. And also on the right-hand side, you can see the hardware configuration that I have used. And it's basically not the freshest hardware that you can find. It's not the most expensive one. OK. So, yeah.
Can you pull the microphone a little closer?
This one?
Can you pull that closer to yourself?
Like that?
Yes,
OK.
Thank you.
OK. OK. So, oh, yeah. Now I hear it. Yeah, actually, I thought that this microphone works only. Cool. So I hope that you did not skip the previous slides. Cool. So the fact is that indeed you can take advantage of native BLAS in Spark, and you should do it if you do some linear algebra, and in particular matrices multiplication. The last part of our requirements is scalability. So as I mentioned, we addressed efficiency by using the batch processing and using native BLAS. And scalability is more tricky thing. As I mentioned before, the parameters of the model are estimated with the backpropagation algorithm. And this algorithm is iterative, so you have to do plenty of iterations. and on each iteration you update your model. And I'm going to briefly explain this process. So on each iteration, each node gets parameters from master. So in a single node case, it would be just one executor that gets a parameter. And that's represented on the left-hand side. So those parameters are the weights of the model. Then on the next step, each executor computes a gradient given the data that it has locally. And that might take some time. After that, it sends each executor sends the gradient to a master. And at the end, master computes new version of parameters based on the gradients. And it can be done in different ways. And there are different types of gradients, actually. Like, for example, batch gradient, when you process all data on each iteration. Stochastic, when you process random point. And mini batch, when you process random batch of data. And I'm going to talk about the batch gradient. One of the reasons is that stochastic is very hard to parallelize. It's basically a sequential algorithm. But we are also looking into it. So the next question is how many workers to use. So it seems that if we have less workers, then we can do less compute, obviously. But if we have more workers, then we have more communication. Because we send the parameters on each iteration, and we can have millions of iterations, and we can just defeat the purpose of more workers by spending a lot of time on communication. So there is a computation trade-off here, obviously. And let me talk about it in details. So assume that we have a data set with D data points, F features, and K classes. And we want to train a logistic regression for simplicity. It has Fk parameters, which is features times classes. And we can write the formula for communication and for computation in this case. So for communication, we have n workers, and they get and receive Fk 64-bit parameters. So it's double precision. Or you can have Fk 32-bit parameters if you have single precision. So they send those parameters through the network with a particular bandwidth, B, which is usually 1 gigabit or 10 gigabit, and some software overhead, C, which is just software overhead that is connected to your software that you use. And in case if you use all reduced pattern for communication, you will end up with the following formula for communication. So in this formula, 2 stands for the fact that you need to get and then to send the parameters. So on each iteration, you do 2 communications. Then 64 Fk divided by B is just the number of seconds that you need to transfer one set of parameters. And C is our overhead. Logarithm stands for the all-reduce communication pattern. So if you have used simple communication pattern when you send parameters at one time, as I have shown on the previous slide, then you would have n instead of logarithm, which is worse. Then for computation part, each worker has p flops. So it has a CPU, and this CPU has p flops. And the worker should process d divided by n of data. So I assume that the data is equally distributed over all workers. We have n workers and d data. So each one has d divided by n data. And it needs to do 2 Fk operations. And it's basically multiplication of matrix and a vector, matrix of parameters and vector of the input. And based on these estimations, we can write a formula for the computation. So it's d divided by n, you parallelize by data on your workers, and 2fk divided by p is just the number of seconds that you need to spend on computation. So it's rather simple formulas. And then we can try to estimate what is the optimal number of workers for a particular data and for a particular model. So we can just minimize the sum of those two times. And if you minimize it, you will come up with such a formula. And we can even generalize it for any model. So this formula is for logistic regression, and the last formula is for any model. So I just replaced 2fk, which is the number of iterations. I replaced it with L. So L is the number of floating point operations for the particular model. And then, based on this formula, you can estimate the optimal number of workers by putting the actual numbers of your data set and the number of weights in your model and the number of computations you need to do, and also the network speed and the number of flops. So let's take a closer look on this formula and see if it makes sense. So more flops means lower degree of parallelism. It is simple because it's in denominator. So the more computations you can do, then the more obvious is the communication trade-off. Like you compute very fast, and then you need to spend a lot of time on the network. So that makes sense. Then if we have many operations, so the model is very complicated, like deep learning. You have many features and a lot of classes and a lot of parameters. That means higher degree of parallelism. So you spend a lot of time on compute, and then network time is not that big compared to the compute time. And if you have a small overhead for sending or getting a message, it also means higher degree of parallelism, just because you save time. So it seems that it makes sense. And I can give an example for the particular data set and a particular cluster. So there is a data set called MNIST 8 million. It's also a handwritten digit recognition data set. It has 8.1 million of documents, also 784 features, 10 classes, and we want to train logistic regression. I have a very slow cluster with 32 gigaflops double precision CPUs and slow network with 1 gigabit and overhead of 0.1 second, which is just an estimation of the overhead in Spark. And if you put the numbers in the formula, you will get that the optimal size of the cluster for training this model is 12, which also seems reasonable. For artificial neural network, we can also estimate the number of operations needed for each iteration. And this slide just shows how you can estimate it, like how to estimate the L for your model. So for the multi-layer perceptron, for forward pass, you will need 2W computations, for back propagation 2W, and for gradient also 2W. And totally it will be 6W. And then you can put a 6W instead of L. So I'm not going to go into the detail, but it's to show that you can estimate the number of operations for your model and then use this number in the formula to get the optimal number of cluster, optimal size of the cluster. in some cases, you may not have this optimal number of workers. Like you may not have like 12 nodes in the cluster or 100 nodes, whatever it will show. But it seems that it is okay, because if you plot the graph of this formula, then you can see that it's after a quick drop, the time decreases slowly. So on the y-axis is the time needed for one iteration, and on the x-axis is the number of nodes in the cluster. So when you have only few nodes, adding one more node actually decreases the time a lot, because the graph drops. But then it starts decreasing slowly, actually, and adding more nodes does not actually provide you a very big speed up. And at some point, even it starts to increase. If you look at on the right-hand side of this graph, it is because the trade-off of computation and communication. You will have so many nodes that they will congest the network, and you will spend a lot of time on communication. So it seems that we can use less nodes than the optimal number and still get good performance, still get good speed up. And we can also estimate what is the how slower is my cluster comparing to the optimal one. Or if I want to be only 10% slower than the optimal case, how many nodes should I have in the cluster? And it's also easy to estimate using this formula. So on the left-hand side, it is the time of your cluster. On the right-hand side, it is the time of the optimal cluster. And after some computations and a little bit tricky approximation, we will get the formula for how much is our configuration slower than the optimal, which is k here on the slide. And also, how many nodes should I have in my cluster to be k times slower than the optimal. And here is an example. So we computed that the optimal number for logistic regression is 12. And how many nodes can I have to be only 10% slower? It is 9. And I think it's a nice result, because you can reduce your cluster by 3 nodes, but the performance will be slower only 10%. And it might be a good trade-off in terms of money and speed. So after all these elaborations on the scalability heuristic, we did the actual scalability testing of the multi-layer perceptron that we implemented. So we used, again, this MNIST dataset with the 60K samples. And we used very deep network. So actually not very deep, but deep network with 6 layers. It contains 12 million of parameters. And it is also taken from one of the papers on about this dataset. We used rather good CPU with 100 gigaflops double precision. So it is a cluster of the nodes with such CPUs. And we compared our implementation with Caffe, which is a deep learning tool from Berkeley, and it is a single node implementation. It can use GPU, and it's extremely fast. And for GPU, we used Tesla, also not a very new GPU, but still what we had. For Spark, so for Caffe, we could use only 1 node. And for Spark, we could use many nodes. And actually, on the slide, we used 13 nodes. So it's not the case that 5 workers that is written here. So actually, we use more. So on the right-hand, yeah?
Can you explain briefly why do you have 12 million parameters? Where do these parameters come from? It doesn't.
Yeah. Uh-huh.
I see you have these 2,000 neurons or 2,500 neurons. So
Mm-hmm.
how do you get millions of rounds?
Mm-hmm. Yeah. So this is the network with 6 layers, and each layer has this number of neurons. But each neuron has more parameters because it has a lot of inputs.
Oh, so each is connected to all inputs
Yeah,
of
yes,
the previous?
yes.
I see. Okay, good.
Yeah, so basically, to compute the number of parameters, you need to multiply
Yes, yes.
784 by 2,500, then plus 2,500 times
So
2,000.
they're fully connected?
Yes. Yeah. So that's how multi-layer perceptron works, as opposed to convolutional networks, for example. Okay. So on the right-hand side, there is a graph that compares the speed of Caffe and our implementation for this particular network and on this particular hardware. And different colors, they represent different things actually. So the green color represents the total time for one iteration of the multi-layer perceptron, and it depends on the number of nodes that you use. And you can see that the shape of the graph is similar to the theoretical graph that we had on one of the previous slides. So in some point in time, you just are stuck with a lot of communication, and the time doesn't decrease anymore with the number of nodes. And it seems that there is an optimal number of nodes here, so like around 5 or 6. And if you add more nodes, you would not gain a lot of speed. The orange line stands for Caffe, so it is a single node implementation, and the orange line is CPU implementation. And you can see that for one node, our implementation is slower than Caffe. But I think it's okay because our implementation is in Scala, and there are also some Spark overheads. So we are not that worse than Caffe on single node, so only 1.7 times slower. But if we add more nodes, we can scale pretty good. Like for example, 5 nodes give us a 4.7x speed up, and it actually beats Caffe on a single node, obviously. It also comes close to GPU, but only in the matter of computations, because you can parallelize computations. But then you will have a very big network overhead, and like on the right-hand side of the picture, and it will just defeat the purpose. So that's kind of is consistent with our theoretical formulas, that there is a trade-off between computation and communication, and probably there is an optimal number of nodes, and you can just use this number without spending much effort on a big cluster. And actually, I can also put those numbers of our experiment into this formula. And if I do it, I will get 15. So formula tells me that 15 number of nodes is optimal for this particular experiment. Yeah, it's not the case probably here. And this is probably connected to the fact that Spark does not already use communication pattern. It has a different one, which is not logarithmic, so probably somewhere in between of linear and logarithmic. And if we use the second formula, which is needed to estimate how much slower are you than the optimal case, it gives us 1.5. So it shows that with 5 nodes, we are only 1.5 times slower than in the case with 15 nodes. So we have a cluster that is 3 times less than the optimal, and the performance is just 1.5 times slower, which is also, I think, useful result that shows that you can still use reasonable size of cluster, and you don't have to use a very big one. And you can try to estimate what is the optimal number. Okay, so let me make some conclusions and talk about the future work. So we have implemented this multi-layer perceptron, and it's available in the Spark since 1.5. So it's not a package. It's included into Spark code. And if you use Spark, then you can use multi-layer perceptron. It has API in Scala and in Python, and it supports pipelines. So it is easy to use. We also provide extendable internal API. And further contributions are very welcome. So it would be good if people will write new layers and somehow advance the state of the art. One of our conclusions is that native BLAS and also GPU can speed up Spark. And if you use some linear algebra computations, then probably you should use native BLAS within Spark. And we provide some useful heuristics for parallelization of batch gradient, which allows to estimate what should be the number of nodes in your cluster for the fastest computation. Currently, there are several new features in progress. In particular, stacked out encoder. Actually, it's finished. It's not yet merged into the master branch. Restricted Boltzmann machines. It's also done, but it's not merged. Dropout, it's in progress. And convolutional neural networks. It's done, but actually, currently, we are optimizing its performance. And for the future work, we look into several different directions. So first of all, we try to come up with some new heuristics how to parallelize the batch gradient, and we look into adaptive LBFGS, and it's kind of interesting thing because as opposed to a stochastic gradient, it has better convergence. It's usually converges faster, but the convergence is proportional to the number of documents in the training set. And if you have a very large training set, then it takes a long time, even that convergence is fast. So we look into ways how to have a different convergence ratio. And also we look into the stochastic gradient and parameter server. So it is another approach how to parallelize the gradient descent. And the asynchronous version of parameter server is not, right now, is not feasible in Spark, so it should be a separate component. And it's kind of another line of research. And also we continue work on new features. And there are many people working on them, and I invite you, if you're interested, also to contribute. And it's very interesting, I think. So thank you very much for listening, and we have time for questions, I think.